Well, I'm very pleased to welcome Eric Miller to the Wilson Forum today. Eric is the chief scientist of the U.S. Department of Energy's Hydrogen and Fuel Cell Technologies Office. And today he's going to speak about a program called HydroGEN. This is the materials research program supporting the United States national priorities in clean hydrogen energy production. Eric has a background in applied physics from Cornell and electrical engineering from the University of Hawaii. He has spent nearly over 30 years in research and development on hydrogen, particularly photoelectrochemical production of hydrogen by water splitting. Eric, I'm just delighted to have you join us today. We've been looking forward to your visit for quite a while now, and it's just a delight to have you with us. Welcome. Maybe I should say aloha, right?
There you go. Thanks, Ron. It really is an honor and pleasure to be with such distinguished colleagues to have this opportunity to talk to you about, I guess, the passion of my life for the past 30 plus years. I think I can start sharing screen now. Is that the process? Let me give that a shot.
Yeah.
All right. And let me know when things are looking about right.
Yes, yep. They're looking right.
Okay, let me get it in full screen mode for you.
Yeah.
All right.
Perfect.
Are you all right? Now let me see. Make sure I can get a pointer going if I can. There we go. All right. You see a laser pointer?
Yep.
Yes. Yes.
All right. Let me begin. Thank you again. As Ron mentioned, I am at the Department of Energy. I've been working in the hydrogen program for quite some time. A lot of the comments that we've just heard about the priorities, what's happening in science, all the exciting fields, hydrogen touches upon a lot of them, not only the technology side of it, but also some of this workforce development, environmental justice. I'll talk a little bit about, actually I'll talk quite a bit about the hydrogen program before I get into the technology programs around the consortia, the HydroGEN and others. So let me get started. Let me find how to do this. There we go. Advancing slides. You seeing this?
Yes.
Okay, great. Let me make sure I can see it and move some things out of the way. Great. Okay, so first I'm going to talk a little bit about what the hydrogen program is at the Department of Energy and why we're doing it, how it's feeding into national priorities, not only for the environment, but for the economy and workforce development and many other things. I'll talk quite a bit about that first. It's a motivation for why we're doing the science that we're doing and how we're excited that the science we're doing does have some breakthrough potential in terms of helping mitigate the climate crisis, helping develop economic justice. I'll talk quite a bit about that because that's a big motivating factor. I just want to first mention that I do have a lot of slides and I talk fast, but I won't spend a lot of time on each one. Once I get started, I'll go through things relatively quickly because I do want to have time to have conversations afterwards to hear thoughts and have some discussion. I do want, there's many resources I can point you to. Two of the more recent ones are the Hydrogen Program Plan for the Department of Energy. It's a great overview of everything that's happening across the department. It's online. You can look at the site here to find these resources. Just recently, actually this year, a few months ago, we released a National Clean Hydrogen Strategy and Roadmap draft, which was out for public comment. The comment period is ended. We're assimilating all that stuff and putting that in. We'll publish that as a full publication in the near future. But I do recommend these two resources if you want to know a little bit more about hydrogen from the national priority perspective. This is a bit of an eye chart here. I have several of these. This kind of shows the structure of the Department of Energy, starting with our secretary now, Secretary Granholm. There's a lot going on in DOE, not only hydrogen, across renewable energy, fossil energy with carbon capture, nuclear energy. All of these offices are a part of our Department of Energy. The interesting thing is that all of them are working together under the hydrogen program in specific areas of hydrogen development. And quickly, let's kind of do this. There we go. I won't go through this eye chart as well, but I just wanted to highlight that the hydrogen program covers all aspects of hydrogen, of clean hydrogen. That's a big distinction. I'll talk about that quite a bit. Not only the production of it through multiple technologies, but how do we deliver it, store it, convert it in cars, but in other application spaces as well, and looking at where that fits into the economy, looking at not only the early days when people were looking at hydrogen powered cars, that's just a small fraction of the opportunity space that we've identified in the previous few years. So I won't spend time on this. I'm going to continue and show you something that we call H2 at scale. This emerged about in 2016 when we were working primarily on developing the hydrogen car. In the early 2000s, there was a presidential initiative to put fuel cell cars on the road. It's very interesting. The hydrogen program, the hydrogen research and development program that I've been a part of for many years, it has been a bit of a roller coaster. It's been up, it's been down. It's got a lot of support by one administration, then the next administration wouldn't like it. We're at a really interesting inflection point now where all of the pieces are coming together primarily because of this picture I'm showing here, this hydrogen at scale bubble chart, we call it. It's been around since 2016. And it really does show that it really couples a lot of different parts of the energy sector. So basically, we've got the energy electricity grid, and we've got the natural gas grid as kind of our main infrastructure for energy in the country. But we were able to decouple that if we were able to produce this clean hydrogen. And what I mean by that is you can use a lot of different sources of energy, renewables, nuclear, fossil. They can either feed into the grid directly, but there's ways you can use these to directly produce this hydrogen in a clean format. That then, we're already using 10 million tons of hydrogen in the United States alone, about 100 million tons across the world, but across different sectors. It's not just in cars. It's in synthetic fuels. It's in making ammonia for fertilizers. It's in metals production. It's in all of these areas that people are using a lot of hydrogen already. The snag is that the hydrogen that we're using, the 10 million tons in the United States today, is all coming from natural gas reforming. And for every ton of hydrogen you're producing from natural gas, you're putting 10 tons of CO2 into the atmosphere from that process. So the point of hydrogen at scale is basically alternative ways to get this hydrogen that does not emit the CO2. And there's a lot of ways to do that. And that's what we're working on, making sure we have the infrastructure to produce this clean hydrogen and to get it around to all of these sectors, as I say, the chemical sector, transportation, as well as even generating clean power for the grid and off of the grid. So, I mean, this is kind of a big important thing to realize about hydrogen, that it's not just for cars anymore. And once that was the case, it became really a bigger priority for the national landscape. And here's just a quick picture of a little bit of what I was talking about. Here's where we're using the hydrogen today. And this is primarily in refining oil, which is not something we want to continue doing forever. But methanol and ammonia production is quite big as well. We're really identifying these other sectors that are expanding the use of hydrogen. But to do that, you have to make the hydrogen. So we're mapping as a part of our portfolio. Mostly all of these dots here are the natural gas reforming centers where there's natural gas infrastructure to make the hydrogen. But what we're starting to see now is these clean hydrogen by splitting water through electrolysis is starting to grow across the country as well. That's what the green dots are. So this is just what we've done in the past. What's on the road today? There's only how many cars on the road, or not that many, but we're really looking at opportunities for heavy duty trucks and buses. There's a lot of investment in that for long haul trucks to use the hydrogen instead of batteries, which is a little bit problematic at those scales. So that's a snapshot, and I want to get a little bit into where we are today in terms of some of the legislation that's going to be instrumental in moving the ball forward in this space. You're probably familiar with recently the bipartisan infrastructure law. It's also IIJA. It's called many things. But it had many provisions, but some of them are really specifically related to clean hydrogen. There's $9.5 billion specifically in that bill for different levels of research, development, demonstration, and deployment of clean hydrogen. And this just is where that's being focused. Electrolysis, which we'll talk quite a bit about later, looking at manufacturing and recycling opportunities. But the biggest one really is $8 billion. Is being deployed as we speak, or being set. It's in the process of being deployed for what's called clean hydrogen hubs, regional hubs, which really is exciting. That we're really looking at opportunities around the country that have certain resources that can make hydrogen cleanly, but also can use the hydrogen and develop jobs at the same time. One of the things I do want to point out that we were talking about before is if you look at the priorities from our administration in hydrogen and across the board. It's not only the technology development, it's not only the climate change, it's also this environmental justice. As important as the technology development is, we're being very, very invested in developing workforce and making sure our technologies are benefiting all aspects of society, not just the privileged few who can afford the most expensive cars. So I just want to keep that in mind. That's a big priority for us as well. How do we serve all communities as well as develop workforce, especially in underserved communities where there's opportunities to bring them into the workforce and into a bigger part of our national priorities. I'll talk about the hydrogen shot later. The other thing I do want to mention is that the Inflation Reduction Act, the IRA, also included some provisions that were really instrumental in moving the ball forward, specifically the clean hydrogen production tax credit, which is going to really incentivize the economics of making and utilizing clean hydrogen. This is the National Clean Hydrogen Roadmap I talked about before. Basically, workforce development, safety, all of these things are fundamental to all the technology development we're doing. We've projected in this roadmap, the current 10 million tons of dirty hydrogen that we're producing a year. By 2030, we're hoping to get all 10 million tons into the clean hydrogen realm. And if we have that infrastructure to do that, we project by 2050 that'll go up by 5 times. The demand for that is increasing every day. So a key part of this is really who's going to target these end uses. How do we bring the cost down? And how do we define these regions? Is there a question? All right, keep going. I know I've got a lot. So we're going to get into, again, another eye chart. There's what we call pillars or thrust of the strategic plan. The thing I'll focus on mostly is this clean hydrogen production in my slides, but keep in mind we're also doing, we have to pay attention to the infrastructure for the delivery and how these end users can affordably transition from the current state of their utilization of hydrogen into the clean hydrogen. And all of these enablers I just talked about are really going to be about the people doing it. Again, just highlight that this once the administration came in and the new administration prioritized climate action, prioritized environment, prioritized environmental justice. The very first Earthshot, and there's several of them at this point, was the hydrogen Earthshot. And they named the Earthshots, I think, after the moonshot, because it was basically, we need to do this now. It's all hands on deck. Let's rally around these enablers to really address the climate crisis as well as all of the other national clean energy priorities. So the Secretary Granholm in 21 launched the very first Earthshot, and that was the hydrogen shot. And like I said, there's multiple shots. The hydrogen shot was first, but they're also looking at energy storage, getting carbon out of the atmosphere, looking at geothermal opportunities and offshore wind opportunities. There's a lot. All of these have been identified as key enablers for saving the planet, basically. Just for the hydrogen shot itself, 111 was the catchphrase. I think if you're seeing my shirt, you see hydrogen is element 1. They thought that was a clever way to put a tagline onto this. Basically, they want to get this basically $1 per 1 kilogram of clean hydrogen in a decade. So I guess it makes sense. For some context, the dirty hydrogen I was talking about is about $1 per kilogram today. So if we can bring the clean hydrogen options down to that same level of cost or cheaper, there will be a natural incentive to move in that direction. So this is what the shot is aiming at, is to really clean up the hydrogen stream of affordable hydrogen. Again, this is in the strategic plan as well. It just shows how 111 can then couple between all of these renewables, nuclear and fossil energy with carbon capture to enable all of these end cases. If we look at the impacts, again, I mentioned decarbonization, equity, resilience on the energy sector, hopefully security as well as jobs. And hydrogen actually feeds into the long duration storage as well. So just keep going here because I know you want to get into science stuff at some point, right? So in the hydrogen shot itself, we've bucketed into 3 pathways that we'll be looking at. The electrolysis is splitting water using renewable electricity. Thermal conversion is basically what we have today with steam methane reforming. But the point there is to add carbon capture to those technologies. And I think maybe the more interesting, but the most intriguing is this advanced pathways that really are the next generation, looking at direct ways to split water using sunlight, for example, without having to go through multiple steps. Also biological approaches, fermentation, microbial electrolysis. So we're looking at really fundamental stuff here that feeds into the basic science that can either enable catalysis or give new insights to improve the other pillars. So that's really a kind of foundational science aspect of this that we've got really some of the best people in the world, in the country, developing these really interesting processes and from fundamental scales. And I'll talk more about that. But really, we're looking at in the near term, how does that benefit us? But how can we get the cost of carbon capture down from the infrastructure we have in steam methane reforming? but really, how do we build up this in the long term? How do we build up this water splitting infrastructure that uses renewable electricity? We're at maybe in the United States about 600 megawatt manufacturing capacity or plant capacity. We need to get to if we're gonna replace everything we have today, it's gonna be on the order of 100 gigawatts of manufacturing electrolysis. So we're just scratching the surface on that. But the point of that is we've got a lot of companies coming out starting this. How do we bring the cost down in electrolysis to really to that $1 level? And that's going to be a big part of the research we're doing. I just want to come back to the fact that it's research, development, deployment, demonstration, everything, all of the above, of course, the things I just talked about, but really it's this virtuous cycle of basic research, looking into the applied research, feeding into the applied research, into the demonstration and deployments, but collecting all that data and really going back, making sure that we're looking at the right things, we're collecting the data. It's an enormous amount of information that's being generated through this process. And we have to make sure that it isn't a virtuous cycle, that people are paying attention to each other, not siloed, which can happen, right? I think we've all seen that. But it really does. There's a lot of foundational science going on that's really informing all of this. And this is just more on the right here. This is just kind of shows some of the funding mechanisms that are in place today, like this $8 billion I talked about. That's mostly for deployments at a large scale. But some of these other investments really are more lower, what we call TRL, technology readiness level. And it's kind of this virtuous cycle. We'll all have to feed into each other. But it also has to be, attract investors to make sure that what's being deployed is not just going to be a one-off. It's going to be sustainable, and people are going to start investing more and more. So this is how we approach it. This is where we find we're in a unique position. This is like it's a make or break time for us. Those of us who've been doing it for 30 plus years have never seen such opportunity as we do today. I'm not going to spend more time on this other than the fact that it's an expanding function. I'll talk again about this HydroGEN and other consortium program. It will be the rest of my talk. But we're really looking at how, are people actually deploying this? Where are they deploying? We've had some early demonstrations coupling with nuclear energy, early demonstrations using hydrogen as a backup power supply for data centers for Google and others. But we're also looking at some of these ports, and actually people are looking at potentially using a hydrogen or a hydrogen-rich compound to replace bunker fuel that has to be replaced because of the sulfur requirements. So it's really interesting to see where we can go and who's investing in these technologies and these opportunities. Again, I mentioned these three, and I'm going to get a little bit into the weeds on them. I'm going to focus largely on electrolysis and the advanced pathways, because the thermal conversion it's there, right? There is a carbon capture research and development aspect of this, but most of what I'll be talking about will really touch upon some of these larger scale, farther scale types of technologies, as well as, how do we split water in a clever way, either from electricity or from sunlight? And I'll go into some of those opportunities as well. The point really is that we need to bring the cost down. If we look at electrolysis as one example, this is the capital cost of the electrolysis. This is what we need. This is what we have to do together to get to the goals of $1. This is where we are today in terms of the capital cost of the systems for electrolysis. We've identified just manufacturing economies of scale to bring it down about halfway, but all of these innovations and research and development are needed, to go stepwise down to this $1 per kilogram. And that's what we've, the analysis shows where can we apply those research dollars for the biggest impact to achieve this in the next 9 years at this point. And now we're going to get into the consortium model. Just a little background on the Department of Energy is one of our jewels is really our national laboratory system. I think you're probably quite familiar with that. The national labs are scattered across the country, but they've got different areas of focus. They've got different areas of expertise. They've got some of the best scientists that we have working at them. What we did early on in the hydrogen program is realize that we can leverage the national laboratories, the expertise, if we organize them in this consortium model. And the organization really was not everyone go do everything. That was kind of the modus operandi at the labs for a bit back in the day. We realized that we needed to pick a topic. And for example, water splitting, and identify the laboratories that are looking at different aspects of that, whether that be the fundamental materials calculations, computational chemistry, or whether that be manufacturing expertise. So we'll talk about how that all fits into the consortium model. The two consortia that I'll be talking about mostly is the HydroGEN consortium, which is basically looking at water splitting. But there's another consortium, H2New, which is the sister consortium, and it just kind of falls along this TRL line where the HydroGEN consortium of laboratories is really looking at the fundamental processes, catalysis, membranes, and other aspects of splitting water technologies. The H2New is taking that to the component and device and system level, integrating those together and looking at the manufacturing opportunities. Once we kind of move that up through that virtuous cycle, the fundamental knowledge is being integrated with between the consortium, and they're learning from each other. Little structure on those, just kind of how that works. This came out of something we developed back in 2016 as well, independent of the hydrogen program. It was something called the Energy Materials Network that we stood up, and it really was centered on this consortium concept that national labs, if you put the right ones together and under an umbrella, a specific umbrella, they could accomplish more faster. It was inspired by, you might be familiar with the Materials Genome Initiative that was back, a presidential initiative back in the day. It was the MGI was really more foundational, fundamental materials, computational chemistry, looking at discovery of new materials or designing new materials from scratch. The office ERE, energy efficiency, renewable energy, looked at that model and said, we can do this, but more on the more applied scale. So a lot of the ERE offices came together and put forward these consortium under different umbrellas. For example, ChemCap Bioenergy Office put together. They're looking at chemicals. Chemical catalysis that makes different products or fuels and so alternative plastic routes and things. Looking at taking biomass and turning that into value-add products using catalysis, unique catalysis. But the first 7 are here. There are quite a few that were looking at hydrogen. I'll talk about those more. But it was just an interesting model that all the offices came together really to accelerate this deployment of innovation into the marketplace. So we really are using this consortium where we've leveraged it quite heavily over the past several years. I'm focused more on the HydroGEN part of it, the water splitting. If we look at what's going on there, it's basically what they've identified, and I'll show this in the following slides. They focused on things at the national laboratories that most people and universities don't have access to, and it's creating that access is a big part of the consortium model, allowing different universities or industries to come in and say, I've got this interesting idea, I've got this project, I don't have this capability, can I jump in and use it here? And these capabilities range everywhere from like basic materials theory and computation, synthesis of the materials themselves, as well as advanced characterization techniques and analytics, so that there's this whole unique set of things that you can do at this consortium that most people don't have access to, and it's really an exciting opportunity to bring the community together under the water splitting umbrella. Basically, I just want to talk what technologies is HydroGEN looking at. It's looking at this electrolysis, which is basically taking electricity and splitting the water. You could do that with 2 nails, right? You could just pump electricity into water, and you'll be getting 2 half reactions. One side you'll be producing the oxygen, and the other side you'll be producing the hydrogen. That's been around for a while. Electrolysis is well known. It's in centuries old. There's ways to do it. Even at scale, back in the early 1900s, there were major ammonia plants that were producing a lot of hydrogen through electrolysis, but the technology was kind of old and it's not so scalable. There's some issues with it. So there's new ways to do that low temperature electrolysis. There's also high temperature electrolysis using solid oxide materials that has much higher efficiency of utilization of electricity. But we're also looking at splitting water directly from sunlight with photoelectric chemistry or solothermic chemistry. So this is kind of the focus areas. All of these things to get to the clean hydrogen. This is what we're the broad portfolio of hydrogen. Again, this is just a picture of that. The fact even in low temperature electrolysis is at least 4 models, 4 flavors of low temperature electrolysis. The liquid alkaline is standard, the old process, but this membrane-based PEM, we call it proton exchange membrane, is kind of the up and coming scalable of the technology of the future that's looking really exciting. The high temperature is solid oxide, and this is just a pictorial image of how you might split water directly with this photoelectric chemistry. There's a lot of semiconductor integration going on here. So I'm glad we've got some experts in semiconductors on the line. The solothermic chemicals is interesting as well. It's a redox material cycle. I'll show a little bit more about that, but there's a lot of materials discovery going on in this space. You basically do a high temperature a metal oxide, for example, you subject it to really high temperatures using concentrated sunlight. The oxygen comes off and it goes to the atmosphere. Then you kind of bring it to a new process and do a steam oxidation process where the metal oxide grabs the oxygen out of the water and the hydrogen is released. So and then you cycle it back again. So it's kind of fun to watch that work. But it's a much more earlier stage than others. So here's basically how the projects line up now and the spaces I talked about. I won't go into them too detail, just to highlight that even within each of these areas, there's really specific fundamental science going on in terms of developing new catalysts. One of the issues, and what is challenges, is that the word, with low temperature electrolysis using PEM electrolysis is basically there's still a need for platinum group metal catalyst to make it work well, whether that be platinum or radium oxide. There's a lot of research going on to eliminate that or at least reduce that quite considerably. So that's just one of the examples, and there's a lot more. I won't go into each one of these, but I'll just tell you that within each subcategory, there's clearly identified focus areas that people are excited to move the ball forward in this area. Again, I think I just mentioned the coupling between HydroGEN. Again, this is, these are the technologies we talked about. This is how we do this virtuous cycle and we go back and forth. So I've said this before, but I keep coming back to RD, D&D. This is a part of our portfolio: fundamental research, demonstration, deployment. There's another D in there: research and development, demonstration and deployment. But all of these things are working together as a unit. And I just want to say that none of this works without the people. I mean, I think this is going to. This is the scientific leadership of the consortium. These are the laboratory leads across the board, but there's some really distinguished people here, and they're well known in their fields, and they're doing great publications. They're getting a lot of patents out of this. So I just wanted to highlight the fact that none of this matters without the people doing it. One last thing on the people. One of the cross-cutting areas that the HydroGEN consortium has put forward, has been this benchmarking, what we found in scientific literature over many years in the field of water splitting. People were publishing without any kind of standards in terms of how they were doing measurements or how they were reporting the processes. I think early on, this consortium came together, brought together this team of people from the labs, from universities, and from industry, and decided to put forward this benchmarking and best practices. So that was kind of an early start of the hydrogen project, that HydroGEN's consortium that's had a huge impact on the industry moving forward. Okay, I don't think I'm going to talk too much about the structure, other than the fact that the way it works, this consortium model, is that we've got these national laboratory capabilities, and part of that is to stand up a data hub that is easy to search. The important part is that we can, we enable industry and universities to work with these laboratory experts and the resources, and we have just mechanisms to do that. This is kind of in the weeds of how we do solicitations, how we award projects that are at universities but are leveraging not only the data but also the resources of the lab. So there's a whole process that it's competitive. People will compete for the honor and I guess to be a part of this network. But I think it's really an exciting opportunity to expand not only workforce development, but bring universities the best people to the table and give them additional opportunities by giving them access to these resources that they would not normally have. Just example of that. This is I think this is which one is this? And this is high temperature electrolysis. So just here's an example of here are the labs in the consortium itself that work in the space of high temperature electrolysis. Here's some of the companies and universities that have projects in that space, and just showing you that the benefit really is exchange of information, and people go to the labs and actually spend time there, access to equipment. And it's really interesting because a lot of the industries have a lot of protected intellectual property, and they want to commercialize these technologies. And so there's a way with the data to protect that to a point, and that's kind of an interesting and important aspect of the consortium model, is that the data hub allows for certain levels of protection of data, because you really do need to share the data to understand what's going on, and then that took quite a while to set up as well. All right. So basically how it works is you go to the website that I just showed here. I mean, I encourage everyone to look at it. It's pretty fun. But if you want to really get involved with this community, what you do is there's this search engine that, what are you interested in? You kind of check the boxes here. I won't go through the demonstration, but hey, what technology are you working in? What do you need? Do you need some, data? Do you need material synthesis? You kind of you check the boxes, and all the various capabilities will pop up that you could use, and then who to contact to see what the opportunities are there. So that's kind of a part of the structure of the consortium itself. That's been very successful. I'm just now going to go into a couple of in the weeds sciencey things about it. I'm not going to spend too much time on it, but I just want to show what types of things are happening. And first I'll talk about what types of capabilities are available in the consortium, ranging everywhere from here's one example is first principles materials theory. Not everybody has access to the computational power needed for these types of models, or the people who know how to use them. And it's not, it's not plug and play. You have to really know your material system to even develop models within these frameworks. So we've developed an expertise as several computational nodes in the consortium, looking at various aspects all the way from DFTs to molecular dynamics, all the way up through integration, looking at multi-physics, multi-scale ways, which is really, really complicated. If those who've done it, is that you can be looking at a single a DFT for an individual atomic system. That's great. It doesn't tell you how it works as a catalyst. It doesn't tell you how mass transfer effects are dominant in certain systems. So having a good foundation of computational tools across that multi-physics spectrum is one of the strengths of the HydroGEN consortium in the world of water splitting itself. Looking at even, can you discover new materials entirely? That's really kind of fun. Another thing, just a couple more capabilities that are available through the consortium that people generally would not have. It would, for example, at San Diego National Lab, one of the capabilities is a stagnation flow reactor, which is able to heat very high temperatures and look at chemical reactions and do very sophisticated analysis. It's largely used in solar thermochemistry, where you need to have those very high temperatures and look at the dynamics. You can look at the thermodynamics as well as kinetics of the materials you're working on to see, to really characterize those under these conditions. This is something very few people in the world have, so it's great that we have this specific capability to people who are doing that particular type of research. Similarly, at NREL, our National Renewable Laboratory, same thing. There's this high flux solar capability they have on the rooftop where you can actually do a lot of, it can be used for solar cells as well, but we're also looking at this direct solar water splitting technologies. It's a really sophisticated way to use the sunlight directly, not do it simulated in the laboratory. It's like actual solar incidents on your process, and really to be able to characterize that, how well you're splitting the water with that sunlight. It's a capability that very few people have as well, but it's available through this consortium. Just one or two more before I get into some of the science things. And on a similar vein at Sandia, this is one of the world-class capabilities for concentrated solar. That's, if you look here, basically you can have access to this tower where you have all of these heliostat mirrors reflecting on it. This is where we could actually simulate the really, really high temperatures for solar thermochemical water splitting in real world applications. But again, there's very few places in the world, in the country, that can do this, but it's offered through the consortium. But they also have simulated sunlight indoors too, with this incredible amount of electricity going into to simulate the sun, the solar incidence in a very precise way and concentrating it. So there's an interesting capability there as well. So I'll go into some science things, and hopefully we'll time to talk a little bit more about this. Again, this is just kind of show some of the successes of across where the projects are that are working with this consortium, specifically just talking about some of their publications, a lot of the disclosures that are going on to make sure that we're moving things toward commercialization. But really, this focus on STEM workforce development has been a key part of this as well. I want to keep coming back to that. Now I'm just going to go just a couple of projects and how it really shows how the hydrogen community is bringing together pretty much from every field of science. In the solar thermochemical, we call it STITCH, solar thermochemical hydrogen production, I think. Again, we know how to do this. There's materials to do, but there's no good materials that both release the oxygen at high temperatures and efficiently oxidize at the steam temperatures. So what they're doing is a fundamental materials discovery, looking at for perovskite structures or others where they can actually substitute, pick substitute sites and put new materials in there to functionalize that in ways that'll improve the process, improve the performance. Since we know what we need to improve, the question is, how do you design a material that can address the challenges or the barriers to that performance at this point? And there's been really, this is a leverage some of the most fundamental computational discovery and machine learning tools that are out there to really look at the composition space for these very complex molecules, because you have to do a lot of different things in different parts of the molecule, function different ways, and we're trying to tune those precisely. So leveraging computational chemistry, leveraging the resources that I talked about at the consortium are really making some exciting progress as well. So that's one example of at Arizona State University utilizing the nodes. A UCSD project, I think you're probably familiar with some of the perovskite buzz that's been going on in the solar cell industry for a while. The perovskite is basically a structure, but certain combinations of materials in a perovskite structure have been shown to be very efficient of solar energy collection and conversion for solar cells in the past. Quite cheaper than some of the other alternatives. There's been quite a buzz around what we can do with perovskites in the solar cell in the PV realm. Some scientists have taken that and looked at ways we can now integrate that into this direct solar water splitting concept. The question, the problem with the materials they have today is basically it's a really exciting material for collecting sunlight, but it's not a very stable material. And keeping the durability of that is a problem not only for solar cells, but more particularly for splitting water, because these semiconductors will be in water, to split it. So basically they're looking at ways of, again, the same way, how do you develop a new materials or discover a new material by taking sites in the perovskite structure and tuning them to functionalize it and increase the durability. So it's really exciting to see what people are doing with perovskites. There's several projects that are actually looking at perovskites. One of the ideas is stabilization through high entropy materials. That's kind of a hot topic as well. It's really hard. It's a hard topic, but people are looking at materials that they didn't think could exist but they're entropically being stabilized and be able to understand that better and look at the materials class that allows for that is quite, is also a part of hydrogen production as well. One of the other areas in this photoelectrochemistry is, again, this idea of stabilization, maybe looking at semiconductor systems based on traditional materials, but such as silicon. How do we stabilize those as well? So there's a Michigan project which has gotten quite a bit of press lately. How do we put coatings on? How do we develop a material system using silicon that will now split the water directly with sunlight? And again, they're utilizing a lot of the laboratory capabilities, looking at fundamental characterization of those interfaces, looking at ways to design those materials using DFTs, and looking at synthesis of thin film protecting layers on top of it. So it really is a great collaboration between the labs and the universities. And similarly, Stanford's doing a thing based on a 3-5 material class. Again, that's actually quite efficient, but it's quite expensive. And they're looking at synthesis ways to develop these multi-structured semiconductors to split the water affordably and stably, looking at the coatings that they need for those as well. Again, they're leveraging a lot going on at the consortium itself in terms of designing the materials, designing those protective films. And I think this is probably the last one I'll do here, and then I'll just get into a few more slides before we open up the floor. So I guess we're back to the perovskites again. So I guess this is a recurring theme. So for those of the semiconductor region, or even the computer chip experts, we have leveraged these quite considerably in these university projects. For example, at Rice, how do you have combinations of these materials? How do you do tandem structures? How do you do protective structures in device configurations that you could split the water just by shining sunlight on them? So that's, so we've got multiple projects in this area looking at different classes of materials. They're all competing with each other, and we don't really care as long as it works, as long as it's efficient, and we've got targets for that. As long as it's stable, we've got targets for that. They're all moving in that direction, and they're all learning from each other. That's another benefit of working in the consortium framework, that they all have access to each other's high-level data that's not protected, and they're all learning from that as well. I'm just going to do a little bit of fundamental science. The Office of Science at the Department of Energy As the HydroGEN program was stepping up the past several years, conducted what they call a roundtable on fundamental research areas that they will help in the HydroGEN program. It was interesting to see. I was a part of that roundtable. Basically, they identified 4 areas that they want to invest significantly in. Looking at electrolysis as one of their fundamental priorities. How do we look at how do we revolutionize electrolyzer systems that can split water? But also, like on the more fundamental levels, like how do we manipulate these interactions, these interfaces, where hydrogen is a part of the either being produced or moved or stored. Looking at those fundamental interactions of hydrogen with other materials, looking at, again, these complex interfaces at the atomic level to see if we can use those models that we have at the consortium to develop and discover new materials that are better. And a big focus is on this degradation processes when hydrogen is involved that I talked about quite a lot. So fundamental understanding of the degradation processes in order to mitigate those are all a part of the foundational materials and science. And just one last thing I'll talk about is that we really work across from foundational science all the way to putting it on the roof and getting these things commercialized. So we work closely across the department offices, not only to look at those foundational materials, how do we discover and develop them? How do we synthesize them? This is a basic science work done in I think it was the JCAP hub, a solar fuels hub back in the day. They then moved on into the HydroGEN consortium to help them characterize and then move them to the desk, to the tabletop, then move them to the rooftop to do more detailed characterizations on how they would actually work in real world systems. So it's all of the above. It's all hands on deck. I encourage everyone to go to the website, and it's kind of fun to play with it. I'm going to wrap up so we have some time for conversation soon, but I do want to highlight there's a lot of opportunities if you're interested in this space. I always have to say this, that I was probably the first person to introduce this maybe 5 years ago, and I guess I'll do it again. There's a congressionally mandated National Hydrogen Fuel Cell Day on October 8th every year. Okay, I'll have to say it. The reason they picked October 8th is someone told them that the atomic weight of hydrogen was 1.008. And so they decided 10/8 would be a good day to celebrate hydrogen. And I apologize for that. But however, for us, it's really the diatomic hydrogen that makes a difference. So I'm a little concerned why it wasn't 2016. But in fact, the first time I said this was in the year 2016, and actually I declared that National Hydrogen Year. So that's how I got around that one. But there's also we've got some open to the public annual merit review every June. This year it's coming up in June. Everyone's welcome to virtually or come in person to that. But there's just a lot of resources out there, and there's a lot of buzz in the United States, but across the world in this area. Everyone's really excited to be a part of this community. And I rushed through it, but I do want to have time for questions and answers and discussion. So I hope this is okay to leave it here. Thank you.
Yeah. Eric, thank you. That was a very comprehensive overview of a national effort to try to move a technology forward. It's not easy. It has a lot of tentacles, and you've demonstrated just how complex it can be, but how focused it can also be. And I appreciate that.
Absolutely.
I want to make one comment, and then I have a question. We will have one of your principal investigators speak with this group. This is Ismail Dabo from Penn State University, professor at Penn State University.
Right.
He is someone who is studying materials, I think as part of the Material Genome Initiative.
Right.
And materials for photocathodes for water splitting. So I think it will focus that very nicely when he speaks to us, I believe in May.
Great.
But yeah. I do have a comment, a question, I guess. I think when I think of the most abundant resources on this planet, they are water and sunlight. And at this moment, they're both free, they're plentiful. There are no geopolitical boundaries. There are no international confrontations about either of them at this point, as there is obviously with natural gas and fossil fuels. It just seems to me that water splitting using photoelectrodes should be a major focus. And I know it is, but I wonder in terms of the roadmap, the strategy and roadmap that you have identified, there are a number of different options to producing hydrogen.
Right.
But I wonder whether they are prioritized in some way that might emphasize water splitting, because frankly, it just seems to me it has all the right characteristics. And, frankly, I hope that someday an American president will step up to a microphone and say something like, I am going to announce this nation's commitment to a hydrogen economy. I hope that happens. But tell me, are they prioritized, these production methods?
Yeah, no, it's a really good question. And yeah, answer is yes. We spent a lot of time on that, and it's evolved over the years. Certainly your point to the resource, the solar and water resource, certainly people have looked to that, because we need to get away from, pumping things from the ground in a non-sustainable way. Looking at what energy, vectors, resources we have available. Solar has always been like the thing, right? The challenge, and I'll use that word, it may be problem, is that sunlight, we know that there's enough sunlight hitting the earth for most of our needs, right? I mean, people have done these calculations for a long time. It's a solar cell industry. The challenge is really that it's a very diffuse energy source, right? As it hits earth. So you have to really have a lot of land area to collect enough of it. Whether you're doing that through photochemistry or just even a solar cell. And so we recognize that. So there's certain places where it makes sense to do that. You can't be, coating a lot of places with solar cells at the levels you need to get the energy you need. But that's kind of a part of the puzzle piece, right? Where do you have land area that you can spread out to collect the sunlight? And that's, like I say, that's also part of where do you locate solar cells? Where would you locate hydrogen production plants? The water thing is also quite interesting too. Certainly water is abundant, but it's not infinite too, right? So you have to pay attention to how much water you're using to produce your chemicals and your fuels. People do bring it up, oh, you're splitting water, you're going to be using all the water up. Just put that in perspective. The water, there's a lot of energy in the hydrogen. So you're getting a lot of energy from a relatively small amount of water. But if you're making the hydrogen itself as a chemical carrier, as a fuel, per kilogram or per gallon equivalent of, per energy equivalent to gasoline, you're basically using the same amount of water that you do to make gasoline. There's a whole steam process involved with we're making the gasoline that uses a lot of water too, and it's about 5 gallons per kilogram of hydrogen, so similar to what you use for what we're using today for gasoline. So it's not a showstopper. It's something we know how to do and use it, but you do have to be cognizant or be aware of where the water resource is available, for that process. Then the question becomes, how do you do it? In the past, we were looking a lot to the photochemistry, direct splitting. There's challenges and opportunities there as well. But what happened in the past several years is solar cells became cheaper and cheaper and cheaper. So there's a near-term opportunity just to take solar cells and then hook an electrolyzer up to those, basically because the electricity cost is coming down quite considerably by the manufacturing scale of let's say, silicon solar cells. So there's an opportunity in the near term to develop those couplings, looking to the future where the more efficient systems for direct water splitting can come to play. But we're prioritizing both, right? We need to do the near term things to get it out there, but we also need to be looking forward to the next generation that could do it better.
Sure. While you were speaking, I see hands up, and I will turn to one final comment. I mentioned 71% of the Earth's surface covered by water. When I've traveled in the Middle East, I've been so impressed by the fact that most of their water is produced by potable water is produced by desalination. Mm-hmm. It would seem to me that a lot of I know there are contentious issues associated with water supply. You just look at Western United States. But the fact of the matter is, most of the continents are surrounded by water. And if we started practicing desalination on a global scale, that would seem to me to eliminate a lot of the tensions about water supply, and at the same time solve some of our energy problems. But that's just an observation. That's good. No, it's a good one. Let me turn to Eddie. You have your hand up. Eddie, you're muted. Yep.
Yes. Actually, I think Jenny Wang had her hand up before I did. So excuse us. But I think one of the core issues is why hydrogen? My mind on this is that essentially hydrogen is a very useful fuel for basically a bit like a battery. essentially, that you can take it anywhere and use it anywhere. It's also potentially possible for manufacturing artificial fertilizer and other areas that you can't really do directly with things like just electricity. But I think one of the main critiques I've heard of it is that essentially it's an expensive product, but where is its real advantage when you put it into this energy infrastructure that we're trying to get to in the 2050s? How do you see that?
Yeah, no, good question. I think coming back to, it's an expensive product, but it's not today, right? But today is the dirty high, so that's kind of a part of this idea of transition to not just hydrogen, but to clean hydrogen. So, I mean, I think even, without any advances or new technology or new end uses, we've got a lot of use for hydrogen that if we do that transition, bring the cost down of the clean hydrogen to where it is today on the dirty, what I call dirty hydrogen, there will be a huge decarbonization benefit just from that alone. We're doing that analysis of just by transitioning the current industries from dirty to clean hydrogen. Once it becomes, economically affordable or competitive, it has enormous advantages already. But then what we're doing is projecting into the future, whether it's going to be new fleet of trucks or with the new end users of the new sector uses are looking for the clean hydrogen to be available before they invest in that infrastructure. So, we're projecting a lot of new uses for it once there's an availability of the clean part, because everyone's looking for the cleanness of it, right? No one wants to continue this chemical production method that's polluting and putting CO2 in the air. And it's really important because like I mentioned, there's an electricity infrastructure, but we also look at, where is it useful to move energy and chemical bonds versus electricity? I mean, they're both needed, right? If you're storing it or for moving it over long distances, sometimes a chemical form is a lot more stable and more affordable than just electricity transmission line. So all of these things come to play, but that's why the hydrogen shot to bring the cost down to $1 is the enabler that will automatically transition to some of these decarbonization opportunities and then open new doors as well.
I guess the question still remains in many people's heads is, for example, take steel production. Why use, a gas like hydrogen to, let's say, melt the ore versus just simply electrical means directly?
Right, and that's one of the opportunities. You're right. But there's also the hydrogen is not only for heating, but it's a reductant in some of these processes. So it's it could be foundational to new ways of making steel, or that people are exploring as well. So those are the emerging opportunities as well.
Okay, so I see it really as an emerging technology that's really still got a long way to go. I think
for steel,
to prove its worth. That's a sense I think a lot of people get. But
I think that's a good point. Obviously it does have a long way to go. And what you heard this morning, I think, was a very clear statement or comprehensive statement, both of what it takes to get there and what's being pursued as a national priority. So I think I'm really glad we heard that. I'm looking at, I have 8 hands up, so I'm looking at Jenny. Jenny, you're next.
Okay. Thank you, Eric. Thank you. Such an immense amount of information you just give to us. I don't know where to start in terms of question. On the one end, it has a deep science and chemistry studies, in the sub-lattice level in order to make the feasibility. On the other side is end use. So I'm looking at the end use. You have a considered to be mobile energy generation or stationary energy generation. I would make a guess, perhaps the stationary will be, come first. And I'd just like to know from your deep experience and the vantage point, what it takes to make a mobile generation, what is an enabler? And related to that, if we look at the global industry, basically, we look at manufacturability. Cost certainly is one of the most challenge. So where the the U.S. stands in comparison with the other developments, such as I give one company, for example, Siemens.
Mhm.
I think they are pretty strong in developing the green hydrogen. And so how do you see where they are? How do you see where we are at this point? I know you have alluded, in the things. I just like to have a little bit of a elaboration of where we stand on those issues.
Yeah, great. Yeah, thanks. I mean, so just a couple of points on the first thing, the stationary versus mobile. I mean, this is an interesting opportunity here as well, because one of the opportunities is to store the hydrogen. I mean, use it as a energy storage mechanism, and that's can either do that. There's actually some salt caverns you could use. They do have compressed air, but if you do it with hydrogen, that's like 100 times more energy in it chemically. So there's opportunities stationary where you have like a certain amount of storage or mid-duration storage that you could use, and then you can convert it to electricity and either fuel cell very efficiently or combust it and cleanly as well. But looking at with that in mind, that one of the challenges is even if you make it affordable clean hydrogen, you have to think about how you're moving it, how you're storing it. And that's a challenge for gaseous, because you have to compress it to high levels to get that energy density, or you liquefy it. But both are a bit challenging. But the other option is some of these concepts of just synthesizing ammonia or synthesizing methanol as a fuel or a carrier of the hydrogen. But basically, as long as you're using clean hydrogen to do it, you're also decarbonizing those processes at the same time. Because that's where most of the energy and the CO2 emissions come in those processes is coming naturally. If you use natural gas as the feedstock as opposed to clean hydrogen. But we're looking at that. We're seeing where that might be a part of a bunker fuel, or that the hydrogen itself. People have actually done this. They've had liquid hydrogen tankers going between Australia and Japan. That's worked, but I mean, it may. They're also now looking at ammonia as the carrier, like synthesizing the ammonia with clean hydrogen, calling clean ammonia, green ammonia, and then extracting the hydrogen or using the ammonia fuel itself. So it's complex on that. I mean, but we're seeing where it goes, and we're letting industry lead what they want to do in some of these spaces. In terms of international, I think now with the program I laid out, the United States again is taking the forefront in terms of R&D. The companies you mentioned have been really exciting. Have been doing it. They had a little bit of a head start. But we're seeing American companies now starting to build up their infrastructure, and we're starting to be more competitive and actually starting to take the lead in electrolyzer technologies. As new companies springing up all the time. They're building manufacturing plants, and they're all looking at these clean hydrogen hubs, which now are under review, because there's going to be an enormous need for these technologies to come together in a community to show that there's actually benefit to having them there. So. We're excited. We think that the United States is now poised to take the leadership role in this space again.
Good. Thank you, Era. Let's go on to Albert.
Yeah. Hi, Eric.
Hey.
A couple of weeks ago, the local paper here, The Globe, had a controversy about the safety of using hydrogen in the home as a replacement of methane. And the University of Massachusetts Lowell said it's safe, and a number of other professors from other places were questioning that. I wonder, what do you or DOE stand on that usage of hydrogen in both
Sure.
the heating system and the stoves at home?
Yeah, absolutely. Certainly there's all these enabling things I mentioned before. Hydrogen safety has been one of the key enablers that, making sure that we're documenting the safety of hydrogen, we're understanding it. There's actually a global center for hydrogen safety that AICHE has put forward with one of our national laboratories. That really is kind of the place to go for all things hydrogen safety related, all the studies we're doing, all of the information that's available. No one's going to invest in technologies if they don't have a comfort zone of the safety of it. But it depends on the end use, right? So one of the opportunities that Europe has explored recently is injecting clean hydrogen into their like natural gas infrastructure, sort of blending it to kind of green up that natural gas a bit. The question there becomes then, how does that affect the appliances? How effective are they? How safe are they? There's been a lot of studies in that area. And some countries are actually thinking of transitioning to a full clean hydrogen, gas infrastructure, like transitioning their gas infrastructure to pure hydrogen. That's where this comes in specifically. If you're actually using pure hydrogen, in your stoves and other things, that's where the studies have to come in. I mean, it's under, they're under development. I mean, I think there's no fundamentally more hazardous aspect of hydrogen versus natural gas. It's just that you have to understand that and design your equipment to make sure that you're addressing that. And that's what these international safety centers are doing at a foundational level. So we believe that there's engineering solutions and people are learning about that and addressing those appropriately.
On the safety part of ammonia. Ammonia is toxic, and I see people saying we're going to use it to carry hydrogen, and it's not a very efficient way of carrying hydrogen because the N is so much heavier compared to the H3 in the ammonia. So what's the excitement about ammonia?
Well, why are they doing it, huh? I think a part of the reason is ammonia itself is a product, right, for fertilizer. So there's that. But as a hydrogen carrier, that you have to talk to the shipping industry why they're looking at it. They're also looking at maybe just combusting the ammonia itself. So there's options. I don't know the answer to that one, but we're watching what the industry wants to do.
Thank you.
Thank you. Tom?
Building on Ron's initial question about using sunlight and finding it very diffuse, has there been any looking into the possibility of unfolding a 500 diameter mirror in space and a series of these made of very lightweight film to reflect and concentrate sunlight on Earth to bring about much higher energy levels?
I am not aware of that, right? I mean, I think it's an interesting concept. I think I've seen some proposals, but not in our office, right? That's not really the hydrogen space. That would be under the the solar energy conversion space. But yeah, that's interesting. I am not aware of any specific projects in that area, but I'm interested to see if anyone on this group has a knowledge. I'm glad to bring it to the table. Yeah,
just to comment on that, Tom. I think people have been able to demonstrate that you can split water with natural sunlight using semiconductor photoelectrodes. The problem is the sunlight also splits the photoelectrodes, so they're not very stable. The need is for a durable, stable photoelectrode that would take natural sunlight and has the right electronic properties to split water. It can be demonstrated. It's demonstrable. It's just that it's not stable enough to provide a long-term source. Eric, do you want to add anything to that?
Yeah, that's right. But also, the other pathway is the concentrated solar pathway, right? That's the other stitch I talked about. That's it's a similar material challenge, but different material class. Yeah. That's where we see these mirrors reflecting up on a central tower in the desert, and that's where that would happen. But I think it's a really good point to look at concentrating the sunlight, into a smaller area. Yeah. So you don't have to take the whole of Siberia or whatever to get into your electricity. Yeah. I mean, it's a challenge, but it's an interesting opportunity and creative solutions such as that should be explored.
Gotcha. Michael.
Just a few comments and maybe a question. When you talk about water splitting using solar cells, I think you have to look at the life cycle analysis and go from the mine to the recycling of the solar panels. Right. And see really where that gets you. Secondly, the issues of transport, metal embrittlement, high pressure, seems to make it not likely as an auto fuel. But we've been doing some work with other inventors, and I would add that inventors are the largest research and development department in the country.
Yep.
And we're the most ignored as well, because trying to get into organizations like yours is a barrier to us. Some of us don't have the wherewithal to understand even that process, but are very focused on new technology. So unfortunately, you miss out on a lot of work being done. One of my associates is mixing hydrogen with the fuel stream, feeding diesel vehicles, and having some pretty interesting results in burning out carbon and reducing emissions. And it may be that better than trying to figure out how to produce pure hydrogen for transport uses, it might be better to create a device that you can put in each individual vehicle that will electrolyze the hydrogen enough to add, it only takes 3 or 4% to have an effect in the vehicle. The last thing I would say is anybody doing any work on Brown's gas? Are you familiar with Brown's gas?
Sure, that's it was kind of sort of like town gas back in the day. Is that about right?
No, actually, Brown's gas is what you get when you move the electrodes, the cathode and anode, closer to each other than normal electrolysis. Once you get within 3 millimeters, you begin to notice some interesting thing happen between the electrodes if they're flat plate electrodes. Maybe with a KOH dip will help with some sandblasting, but the gas is very unique. Actually, it doesn't.
Yeah, I've seen archives, and I know that there has been some exploration of it. I have to go back to the archives to see where that stands, but yeah, I'll look into that as well. We're definitely open to innovation. Like I showed this whole spectrum of funding mechanisms. One thing we did stand up just last year was something we called an incubator prize, which you should keep an eye on. We'll see. That's kind of like for people who can't normally get into the process of getting funding, because it's all sorts of paperwork and you have to have all sorts of clearances and things like that. But this is really, people would be competing with more innovative inventions at that scale. So there's a mechanism we've at least just started, right, to get the inventors, give them an opportunity to show their stuff. So keep an eye out for that. We just started it last year. We've got the first round. We'll be having more rounds of that as well. Is
that a website that you listed the entryway to that program?
I'm sure you could find it there. I'll find the actual, the sub page for that and send the link to you.
Yeah, if you could send it to me, Eric, I'll circulate it to all of this crew, because I know there are a lot of very creative and inventive people on this call, and it might. The one thing that I think Michael raised, a very important issue, the individual inventor and innovator, it doesn't sound like there was initially a path for that kind of informational feed to get into the programs that you've mentioned. Right. I think it's an interesting point.
Absolutely.
So if you send me that information, I'll make sure it gets circulated.
Okay, we'll do.
You talked a lot about water as a source of hydrogen. It occurred to me to ask perhaps a naive question. Hydrogen is the most abundant element in the universe, and it occurs in all sorts of biological materials. Has anybody looked into whether there could be a source of hydrogen in any kind of biological matter that might actually be easier to access in terms of energy requirement than even water?
Absolutely. I mean, I just focused on the water splitting part of the hydrogen program, but there's others like maybe it falls under the thermal conversion. But one of the examples of that is our offices are looking at extracting hydrogen from waste streams, for example, and that tends to be biological processes such as fermentation, maybe microbial electrolysis. So there's a whole pillar in that space also looking at those opportunities, and they're going to be more regional, like where do you have those streams or those biological streams, or and we have a biomass conversion, pyrolysis or other gasification processes that work as well, but then you're sort of competing for the biomass, right? So there's going to be regional solutions that use biomass or waste streams, and usually with either thermal or biological processes. But we definitely have portfolios looking at that, but we look at those as more of regional niche production places, because where those resources are available. Whereas water tends to be a little bit more universally available.
I don't know. Is there much competition for the waste stream?
Well, I mean, what you have to look at though is, if you get hydrogen out of it, are you actually cleaning up the waste stream at the same time, right? Are you doing two things at the same time, and then it might be a value add if you actually can show that process works to clean it up as well as just pulling some hydrogen out. So we're looking at it.
Yeah, very good. Wayne, you're next.
Hi. When everything is considered, have people really weighed the comparative advantages and disadvantages of fuel cell powered vehicles versus EVs? I say that because most of the comparisons are just based on efficiency, where EVs are superior. And I noticed that you had fuel cell powered large trucks, and that's probably because the weight of the batteries becomes a problem. Right. But there's a lot of externalities with, as economists would call them, with EVs that you don't get with hydrogen. There's of course the charging time, which people are working on. You know, they keep talking about setting up all these charging stations, but if 3% of the population has EVs now and it goes to 100%, and it takes an hour to charge, well, when you fill up your car at a gas station, it takes 5 minutes. So you can imagine the number of charging stations. There's still battery flammability issues. I know people are working on it. There's recycling issues. And if they can't recycle, then there's disposal in landfills. And there's strategic issues of sourcing. And when everybody talks about the pandemic and the supply chain, most of the batteries are processed in China, and the cobalt comes from the Democratic Republic of Congo. And so there's all these other factors besides purely efficiency. Are there discussions? And do you think that the government has a plan to address all these things when they talk about switching over to electric cars in 5 or 10 years?
Yeah, that's certainly, you might imagine we've had these conversations in the department. I mean, interestingly, as a federal employee of the Department of Energy, what we do is we offer options to the industry. So we have to be a little bit agnostic as about promoting one. We just have to make sure the options are available, and then the markets will adjust. But what we do provide is comprehensive opportunities, not only through the technology development, but analysis all the way cradle to grave, right? Life cycle, looking at what are the environmental impacts from, like even the solar cells you mentioned, right? We factor all of that in when we do not only the techno-economic potential for these technologies, but do this full, cradle to grave life cycle assessment of how much environmental damage are you doing, by the time you get to the endpoint. These are all publicly available. We've done it for batteries. We do it for all technologies across the department. I will say that recently, just last week, I think there was like a transportation decarbonization strategy roadmap that we released. You'll see that there's not a whole lot of hydrogen there because, what people are tending to see is that although the hydrogen fuel cell cars the lightweight cars are out there and people like them, really the industry is moving toward hydrogen in those heavy duty vehicles, basically exactly what you said, because they don't see a pathway for batteries at those scales. So they're really investing a lot more in that right now. So, but if that infrastructure comes up, we'll see what happens. But the opportunities are for fuel cell cars at every scale to be there. It's just the markets will adopt them based on the relative advantages, like you mentioned. And we just provide as much information on that from the department in terms of analysis to help guide that at this point.
As I heard Wade's question, it just occurred to me it would be interesting to know what Secretary Granholm would say in response. And do you feel, Eric, do you feel that you've got the political will behind you in terms of this effort?
At this moment, yes. Right. I mean, you'll see that the secretary announced this Earthshot. We actually gave her one of these hydrogen shirts at a recent event, and she stopped the whole event and put it on top of her shirt, and it was like,
how do I get one of those? I like it.
Let me know. I'm sure we got some more. But right now the secretary, I mean, but it's all the above, right? It's a all hands on deck, whether that be offshore wind, whether that be the hydrogen as carrier. Definitely now, yes, we've got the political will and the investment opportunities to do it. So as I said, it's now or never for all these things to come together.
Yeah. Eddie?
Thank you.
Yes, I'm going to go a little science fiction-y, I guess. One of my dreams has been to be able to take hydrogen, squeeze it down and turn it into metallic hydrogen. Now you've got
you're not alone.
a huge energy density capability. If you combine that in space by capturing protons, which are always coming from the sun, you almost have an endless source of energy and an ability to just transport an enormous amount down to the surface. I don't know if anyone's looking at it, but that's my kind of speculative.
But to your point, though, I mean, this is why we have this whole fundamental science aspect of it too, right? I mean, there's going to have to be really fundamental discoveries on how do you manipulate on the atomic level to do that. But we've got people looking at that at the same time we're looking at these deployments. And you've also probably heard that there was, fusion finally broke even, right last week or something. I mean, it's the same thing. I
Well,
mean,
that was NIF. Yeah, that's been done by tokamaks in the 90s.
but yeah, right. I mean, it's the same kind of a thing, right? I mean, that's a manipulation of hydrogen too. So the more we learn, that foundationally, maybe the next thing is gonna be that. So we'll keep an eye on it.
All right, Albert, you have the last question.
Yeah, very quickly, I want to expand on that political will part. You're planning programs for 5, 10, 30 years. And what if the administration changes? What happened to these programs? Can you tell us a little bit about the thinking?
Yeah, I mean, I think I'm optimistic to the point where, I mean, I've been in the department. I was recruited out of Hawaii to come to the department about 12 years ago. So I've been through a couple of administrations, and kind of the priorities do change. The interesting thing is hydrogen has always found a way to be a part of the conversation, whether that be for its decarbonization potential or whether that be for economic growth and jobs creation. I think we've laid that foundation that there's multiple benefits of it that all administrations have some interest in. So I believe that would be the case again. But I think more importantly is that the current investments we have through these recent legislations have a 5-year lifespan. I mean, the money's already there, right? It's been committed and it's not going away. I mean, so we at least have those 5 years, independent of what administration changes, to work on those projects. And there's quite a lot of investment there. So that's at least gives us a bit of a stability over a 5 to 10 year period of the funding that we have already committed to this. So I'm encouraged. I'm optimistic that that's not going to be a showstopper.
But is the commitment 5 years or 10 years?
Well, I mean, it's 5 years appropriated, but a lot of these projects will go beyond that 5 years once the money's, once they have it. So I mean, it's a 5 year, every year we allocate some of the money and then it'll be allocated within 5 years, but it could be spent beyond that in some of these projects. So yeah, 10 years is our hydrogen shot, and we're just gonna make it happen. So
I just remember that President Carter had solar collector on the White House, and I remember President Reagan and Nancy said, "Let's take the claptrap out of the White House," and that's one example. The other example is during Bush, there was a big $1 billion push on the hydrogen car,
right,
and that went nowhere. And actually, I worked on the hydrogen aircraft in the late 70s, and Boeing had the design, and McDonnell Douglas had the design, and we were comparing the safety aspect of the two. So things come and go. And having said that, are you still that bullish about your program?
And I'll just say this. I mean, back to the Bush administration. I wouldn't say nothing came out. Actually, the technology development of fuel cells that came out, I mean, even though, it was all that $1 billion didn't go into this, but that really did enable the cars that are on the road today. I mean, that's technology was result in a product. So, and then those, that kind of helped us motivate moving into new projects. So maybe it's not all that efficient, but it's definitely, it's something paid off from it, and we're going to leverage that as well.
Okay, so I lied. One last question. You're going to close the comments today. Go ahead.
Yeah, thanks. Since we've sort of gone a little bit into the ethereal and atmospheric, we talk about splitting water. A naive question: is there any possibility of splitting carbon dioxide? If you broke up the molecules, I have no idea whether the energy requirement is too demanding and what you'd get as a result. But the obvious question here is: they got too much carbon dioxide. Is there any possibility of breaking it up?
Yeah, no, that's a really good question, because in fact, a lot of the processes I talked about for water splitting are in parallel being investigated for CO2 reduction opportunities as well. I mean, some of the photochemistry works the same way, different catalyst, but the basic design structure is kind of parallel to people either splitting water or splitting CO2. The thing you get, the challenges at CO2 is there's a lot of different chains of products you could get. It's getting a selective catalyst to get, basically you'll end up with like a syngas more or less out of that, like CO2, which you can mix, or in hydrogen, which you can use as a precursor to make a lot of things. It's just difficult to selectively do that. But there's a lot of research on that, and a lot of the hydrogen water splitting researchers are also good at that. Is in fact, the new solar fuels hub are looking not only at water splitting, but CO2 reduction into different products as well. So, I mean, I think you're absolutely right. We're looking at all of the above, but they're learning from each other, right? The technologies are synergistic, so that, you know, we're moving forward on that, but it's a little behind on that one because of the selectivity issues for the catalyst on that.
Very good.
Okay.
Eric, I want to say it's been an honor and a pleasure to have you with us today. And I especially want to thank you for your candor and the good humor you showed in responding to a whole lot of questions. This is probably as many questions as we've ever had at one of our forum meetings. And I really do
Great.
appreciate the effort and timing of everybody who's been involved. I promise we finish by noon. We're about 2 minutes past noon, but I want to thank everyone for being a part of this today. Eric, once again, thank you for joining
Sure.
us.
Thank you all. Appreciate it.
Great.
It's
We'll meet
great to
again
meet
in
you.
2 weeks, folks. Take care.
Take care.
Bye.
Bye-bye.